Hey, so good morning. I'd like to start off by thanking Stephen, Andy, and the rest of the organizing committee for giving me my first opportunity to give a keynote at a conference. Woohoo! Um, and I hope I picked a topic or a story that's going to live up to what this conference is going to be, and I think I've picked something that will strike a good tone for the conference. Um, uh, the promise of persistent memory as a technology is that it upends decades of conventional wisdom in how people develop and deploy these systems. So it gives a huge opportunity for new application models. The problem with persistent memory technology is that it upends decades of conventional wisdom in how things are implemented. And I think one of the most prominent places where the conventional wisdom clashes with what people want to do is inside the Linux kernel. So this is a story about that, enabling. So that's me. That's me when I'm pretty happy. So I've been Intel about 17 years, not consecutively. I did a little stint at Facebook. And as Stephen said, I've been working on persistent memory enabling in Linux for about the past 5 years. And for some reason, we're not done yet. But for people in the audience that might not be familiar with Linux kernel development, let me give you a quick rundown of Linux kernel development. It's easy. One of the easiest things you'll ever do in your life. So Intel develops about 10 to 15% of each kernel release. The number of commits is about 10 to 15% from Intel, which is a plurality. Like Intel leads as the most contribution. So with that kind of level of contribution, we get a lot of control over the architecture and the requirements of how Linux is developed. We have pretty strict hardware deadlines, and when things come out, and Linux community they're really sensitive to that, and they're really helpful with us meeting our deadlines with my management and other people's management. It's pretty straightforward. And sometimes I don't know what you've heard, but like when we disagree, it's always cordial, it's always pretty professional, and these things are pretty mild. Of course, that's not true. The architecture of these things is in flight and in flux all the way up until the end. Like the first thing you post is probably going to be rewritten. If it's good, if it's a good idea, it's probably going to be written at least 2 or 3 times before it actually lands. So that adds to the time. There is zero concept of Intel having a timeline for Linux kernel, which is kind of a good thing. Like Linux commits to not taking on technical debt, and they want to do the right thing that's in the best interest of the long-term health of Linux, and not necessarily any individual contributors of what they want. And the disagreements are not mild when you happen to touch this thing that I'm calling the third rail of Linux file systems. So contrast this picture to the one I showed earlier, and this is about how I felt a few weeks into realizing what kind of fight we were in for with this, with what we needed to do for the persistent memory programming model. And I kind of want to emphasize that this talk isn't about hanging in there. A lot of times, if you have something contentious, you can just keep posting it, iterate, and eventually you'll get there. And in this case, this was met with hard, almost like what seemed to be insurmountable objections, and it needed some different tactics and different approaches for getting around, not getting around, but for working with that feedback. So what we're going to talk about today. So I'll finally tell you what this third rail is, why we're grabbing it and holding on to it, and why was the situation different than what typically happens in Linux, where you just kind of iterate and get there eventually. And then I want to give some like hard tactics if you're ever in a technical, because this is the in real life conference, and in real life you have to deal with people, politics, legacy. And so that's what I hope is the in real life part of this talk, and I'll give some ideas and tactics about if you encounter something like this in your work. So what are we talking about here? So this is the upending of convention. This is the conventional way that memory mapped I/O happens in Linux. We have the application that's mapping pages. And behind those pages, they're backed by DRAM, and that DRAM is organized by Linux in something called the page cache. And what the page cache is just copies of physical data that's on a disk on your storage device, and the agent that's kind of mapping physical storage to logical offsets of files is your file system. And so this is how paging works. Probably everyone in the room is familiar with this. We're just copying data back and forth between DRAM and storage. So the new shiny stuff we're doing is this technology we're calling DAX, and to show the new world where Linux and Windows are coexisting. They both called their technology DAX, which is great. So both Linux and Windows have a DAX, and effectively it's this: your storage device is replaced with a PMEM device. It's still a block storage device, but it just happens to be a PMEM block storage device. And what we do is, instead of copying data back and forth into this page cache and mapping it into your application space, this technology just bypasses the page cache and maps since your persistent memory is in memory, just map it directly all the way out to the persistent memory device directly. So what this gives you is the lowest latency. Nothing in between your CPU and your storage. You can do direct load stores directly to persistent memory, and you just cut out your entire storage stack. So one of the asks in the speaker notes was to actually show code. So let me actually show what DAX is in practice. So where we are is inside. We're inside do user address fault inside x86 code, and what all this is doing is we've previously done an mmap, and you've gotten a virtual address back, and this is the code that takes that fault and does something with it, saying, oh, you're actually trying to read-write this memory that you mapped previously. So we look up this thing called a VMA, and that's something that got set up at mmap time, and all it does is track what your virtual address range is backed by. And so that eventually, in the case we're talking about here, we've mmapped a file, and we have a VMA that references a file. And we jump into handle MM faults, which is the kind of the core memory management fault handling that all architectures, so x86, ARM, everybody eventually jumps into this guy. So now we're in here, inside the core of handle MM fault, and we start walking page tables, looking for holes in the page table to say, oh, are you accessing address that was well, if it was already mapped, then you wouldn't have taken the fault. So it wasn't mapped, so we're here, and now we're going to go decide how to fill in the page tables with what you actually want. So we are now. So the way this works is we first try to create. So they call it a PMD and a PTE, which are just different levels of the page table hierarchy. So a PMD can map 2 megabytes, and PTE can map 4K. So what we do is we try to do the 2 meg thing first, and if we can't get it, like if it's an alignment problem or the file system didn't give you a 2 meg line block, we fall back, and we fall back to the 4K case. But so here's the 4K case also in that same function. We jump down to this if they couldn't get the 2 meg thing. So once we decide what kind of fault we're going to attempt to do, all we're doing is looking up through the VMA. We get this VMOps thing, which is a pointer back to how to fill in the page table for this thing. So I'm getting somewhere. So same thing for PT. That was the PMD one. Here's the PTE one. Okay. So we have DAX now in ext4 and XFS, and so we're in this function ext4 file mmap. So this is basically what gets called when you've done the mmap, and it sets up this op structure that's going to tell you how to do the DAX mapping for the file system. And we have something similar for XFS. Okay, so now those callbacks have actually finally done a lot of different work, making sure that the file is allocated and we have space and all this, lots of extra detail. But this is DAX right here in the file system case. So what this line is doing This IO map object is something the file system has put together. The file system has said, hey, you want this part of the file? This looks up the block device it's on and the sector on that block device. Good. So then what we do with that is, in the case of a PMEM block device, we have this extra functionality where we can look up its DAX capabilities. So your SCSI disk doesn't have DAX capabilities. Your NVMe device, although people always make that mistake, NVMe device doesn't have a DAX facility, but your PMEM device does. And DAX Direct Access calls in there and says, hey, for this sector, do you have a physical memory address behind this offset? And it will turn that physical address and how much you can map at that space. And so once we have that, now we can actually go ahead and basically create a page table mapping for that physical address, and pop back off the stack and return the user space. So at this point, now you've taken your file offset to a disk offset to a physical address, turned it into a page table entry, and given it back to user space. And that's DAX. That's the whirlwind code tour of what DAX is doing. We have a similar path for the fallback case, like we can't get 2 meg because of a lot of different reasons. I mean, here's all the reasons, and there'll be a quiz on that one later. But then you fall back and you also can do the same thing basically at the 4K granularity. Great, that's DAX, and that's where we started with the DAX implementation. And I was scrolling around a bit, but the question that none of that addressed was, great, you mapped your data and you can do loads and stores to it, but what about this pesky metadata thing? How do you know that the metadata describing the thing you're touching is actually also persistent? So it was interesting because there's somebody on my team who didn't know what a third rail was, and so this is my definition of what a third rail is. This is an article back from 2009 from Valerie Aurora, who did some work on ZFS, but also some other work on Linux file systems. And she kind of nailed why file system developers, or asked the question, why do file system developers have this obsession with things being on disk? And so I'll tell a story because it's important for understanding the depth of how far back this third rail goes. I mean, it's basically the entire history of file systems, but at least for Linux, I can give you some more details. So this is 2009. I think this is one of the first Linux Storage and File System Summit. And one of the topics at that summit was something called O-Ponies. And O-Ponies was about this change in ext4 where people started losing data because they were relying on the semantic of this. If you do a rename of a file in a directory, and so you write the file with a temporary name, and then you do a rename, and then you crash. If you come back up, they were relying on the fact that if you see the file name, that your data is also there, and that's not a hard guarantee. And so sometimes they're booting up and seeing the file name and seeing it full of zeros, and people got mad. So what O-Ponies was about was application developers basically they don't want to call fsync because it slows things down because you have to sync, and so they want the kernel to give them everything fast and everything consistent, and they want a pony, and we just can't give everybody everything. But if you look closely in this picture, there's me thinking, oh, I can go touch fsync, but shouldn't be a problem. And Valerie saying, no, you have no idea. But the outcome of that discussion is no, there are no ponies. If you do not call fsync or sync before a crash, your data is forfeit. There's Filesystems makes zero guarantees about what's going to be on disk, and prior to calling fsync, like it's not going to happen. And that's it. That's it. So here we come with persistent memory and saying, hey, yeah, so we can store with a single CPU instruction, but fsync is an entire syscall with like thousands of cycles and or like hundreds of thousands, like a lot of cycles. Like, can't we just like have some kind of way to say, hey, I know what I'm doing. I'm a persistent memory application. Skip this over. Like, don't require me to call fsync, which is effectively a mmap flag called map ponies. Like, I want an mmap flag that lets me do what I want, and I know what I'm doing. Hey, file system, get out of the way. And this was the first feedback from Dave Chinner, who basically took XFS from IRIX and ported to Linux and has been Mr. XFS for a long time. And it's good to read in its entirety, but he's basically saying that when things go bad, they usually don't go talk to the file system developer they don't go talk to the application developer because they think the file system lost their data, even though the application did something wrong. And so he's been burned time and time again by people coming and banging on his door to say, hey, XFS lost my data. And he said, no, you didn't, your application did the wrong thing, and they don't want to hear that. And so he ends up having to do triage and damage control in the file system to take care of applications that did the wrong thing, but basically trying to make it safer for applications not to mess up. And so when we say, hey, let's do I know what I'm doing flag, he says, history shows that nobody knows what they're doing. So this is February when we were doing 2016. This is about a year-long saga. So this is the beginning of the saga. But it was interesting at the very beginning. Christoph Hellwig, who's also been in XFS for a long time and all over the Linux kernel, I've been doing storage drivers and other things in the storage stack for a long time, and anything of significance that I've ever done in my career has usually had to go by or near Christoph, and I've had to contend with them. The thing Christoph is he's almost always right, and when he's wrong, he's probably still right. But he said, hey, let's like instead of a I know what I'm doing flag, how about a map sync flag? We already have osync that says make file updates synchronous. Can we do something similar with mmap? And but this is back when Dax was kind of nascent, still pretty buggy, and these two parts of it really discouraged us from kind of even thinking this was a viable path. He was poisoning the water, saying, I'm not sure you should even go there, but Dax has a lot of other problems. Let's work on those first. So that was the opening salvo. But like, if you know the outcome of the story, this is kind of like some M. Night Shyamalan foreshadowing for the plot twist at the end about what happened with MapSync. Another proposal that came along from Dave was something called immutable files, where basically you lock down, like once you've allocated your file, lock it down so there aren't going to be any more metadata updates. So you can do all your load store stuff in a file that's never going to change again. But then he went through and listed like these 6 things that sounded really terrible and really hard to implement, and he said, yeah, so this could allow you to avoid fsync or msync, but like it basically made it also just seemed like a poison problem that people aren't going to want to do this, and it's going to be an administrative headache for these types of files. And Christoph kind of added on to that, and NVML is now transitioned to something called PMDK. Last night I decided to redact some of this, but it's basically going back to the whole idea that as you go to touch this core pillar of the entire file system consistency model for the past forever, bad things are going to happen. And so it was around this time where, like, up until this point, I'd been kind of thinking like, well, we'll get there. And this mail, when I hit my inbox, this was when I was like, okay, how am I gonna tell Andy that his PMEM programming model is dying or dead? And so I started to lose some hope. But I don't know if you've seen, anybody here seen Star Wars? And so Luke's flying down the trench, and he's about to be shot down by these the TIE fighters, and then here comes Han Solo swooping in to kind of give him a breath of fresh air. And so that was the role that Nicholas Piggin played. He had been in the core VFS long time, and then he like disappeared and went to Fusion.io for a while. But he just popped out of nowhere and said, hey, Christoph, Dave, I don't think it's that hard. You just got to do this, and this. I did something like this at Fusion.io, but it was just enough of a breath of fresh air to like reinvigorate us to keep trying. So I'm thankful when that arrived when it did, because it kind of gave us the hope that we could keep fighting and find a way to. It softened them up just enough, I think, for us to keep going. Okay, so this is one of the hard tactics that I want to offer for if you're in the situation where you find yourself unable to make progress with somebody who has an objection with the direction you're trying to go. And so this is the tactic I took. So disrupt the objection. So it's basically fight uncertainty with certainty. So if you look at a lot of those comments about what you can do, it's like I don't think it's a good idea. It's probably going to be pretty hard. But it wasn't like hard technical. You can't do this because X, Y, Z will fall over. It was just it was uncertainty. And so you fight it with certainty, and so you fight FUD with code, and something I like to call the patch grenade. So a patch grenade is a bad idea that could plausibly work, and you just throw it over the wall and see what happens. So a lot of people lament being in the office, like can't just work remotely. And this is one time where being in the office actually helped, because I was describing this problem of like, maybe I can do the immutable file thing. Maybe that won't be so bad. How can I guarantee that this file is locked down, it's not going to move, and I can just do I/O to it without worrying about metadata. And Dave Hansen, who's a very management expert, he's like, oh, that sounds a lot like swap files. Because swap files, you map them, and they can't move around because the core is just writing directly to these file system blocks directly, so it doesn't move them. I was like, oh, this is exactly what we could use. So I wrote a patch and said, hey, immutable files problem solved. We'll just use swap files. And but this is the point. Like I think this is the point in the story where so I woke up. I didn't expect it to go in, but I also didn't expect it to get quite this negative of feedback. But I knew it was dead on arrival, but I didn't know it was like way dead. But my response to this email was a mix between having to walk this tightrope of like keeping Christoph as an ally because he's almost always right, and I just made him really angry, but also keeping my job because I'm signed up to deliver this PMEM program model, and this could be either the death of it or not in this response. And so I really and this is where being familiar with the community, you can write emails like this where you can say, hey, we've worked in the past together before. Please calmly explain to me what are the actual technical objections. And I'm not kidding. This email was I think my career. It could either lose Christoph forever and lose the PMEM programming model or open up the doors. And luckily, it did open up the doors. So we had a discussion about it, and we went through all the technical problems with immutable files. But it eventually kind of put immutable files to bed, and then once that was to bed, we said, hey, what else is there? And it kind of spurred somebody to take another run at what MapSync would look like. And so it was shortly after this flame war about daxfile ended that Jan Kara, who's just been a voice of reason and calmness in the entire Dax saga, but had been kind of waiting. Like he also deeply respects Christoph and was never going to go head to head with him. But the patch grenade kind of got Christoph to actually lay out the technical objections to the point where Jan Kara felt comfortable. I think. I mean, I haven't talked to Jan about this, but my guess is it gave him space to come back in with this. And so there's a lot of text here, and honestly, just knowing it did MapSync and knowing it was from Jan Kara, I already knew it was good. About a few sentences in, and that so I stopped reading about that point and just and kind of felt good that I think we were towards the end of this. So what does MapSync do? It's actually deceptively simple, but I think it's only deceptively simple to somebody who's been doing file system development for a long time, like basically to know what you don't need to worry about. But effectively, all he does is in that IO map code that I was showing before. Yeah. So when we passed in this IO map thing, the file system has determined whether this fault has caused metadata to be dirtied or not on entry. And so all it does is when on this way out of unwinding the fault path, it says, hey, did I dirty metadata? If I did, then just call fsync or fdatasync. I mean, it's actually that's that's simple. It's so sad that it was that simple. But yeah, no. So what that does is now at least the file system is not going to be totally confused about what's happening with persistent memory programming. You map a file with MapSync, and anytime you actually cause file blocks to be allocated, you know that when that fault returns, that the file system has taken care of all it needs to take care of with metadata. And so if you mess up making the data persistent through using the right cache flushes and the right API or architecture features, then that's your problem. But at least the file system has made sure that your files are allocated and correctly set up. Yeah, and so MapSync finally kind of gives us the promise of what persistent memory programming is supposed to be, which is direct load store access to media. So I want to say that if you only take away one thing from this talk, don't mess up your persistence models, please, because this was a hard-fought fight to get the file system to give this little bit of leeway. But if you do mess it up, don't blame the file system because they've been blamed before. But if you do, don't say I didn't warn you about the third rail of Linux file systems. Thank you very much. So I don't know if you want to do time for questions or.
We have plenty of time for questions. I have a question.
Oh, sure. Okay.
Why can't you just make MapSync? If it's just on it when the metadata changes, why can't you make MapSync by default on all the time for DAX and non-DAX files?
Because, well, I mean, you probably could make it for DAX files. I mean, I think some people still want to do the legacy auto models, and there's some benefit to maybe delaying and batching up all that metadata work, but really, it was having an explicit way to say yes or no to I want to do this from user space. Like in the 5.3 in the 5.3 kernel, we had this new facility called the VirtIO PMEM. It's basically a para-virtualized persistent memory device. But all it's doing is, in the guest thinks it's talking to PMEM, but on the host it's just a page cache backed file. But when the guest wants to make it persistent, they have to actually tell the host file system to flush the page cache. And so what we've done is said, if you try to do MapSync on the guest, MapSync will fail. And if mapsync fails, you must call fsync. And so now we can virtualize things and say, hey, your fast path is not available because we can fail that mmap. And we can send, and now we can do things like that where we send real heavier fsyncs and other things over to the hypervisor.
Does that mean that my PMEM applications need to deal with the fact that mapsync will fail, and then I have to write all my fsync code in addition to my normal code?
Yes, and luckily there's a library for that. but yes, no, yes, mapsync failing is a feature that allows Linux to well, it also gives us an out to end the experiment too. Like if the experiment fails and everybody messes up, then maybe mapsync goes away. Like, so don't mess up your persistent models.
It's even with just always. It gets even hairier when it's a remote process, where you have a network in between you and the people. And then you really don't want it on by default because it's expensive. So, but you do need to deal with the error case when it doesn't work.
I think that was my question. What are the performance ramifications of mapsync?
Well, so this is also a good point to plug Nova, because I think Nova doesn't Nova is already almost has like a persistent page cache and can commit things with just pointer updates, right, and small writes. Yeah, no, the performance overhead of it is something to the point where you'd want to treat it like something you set up in advance and not take these dynamically. We have some numbers, but yeah, it's not great because you'd like to be able to take all that at once and not have all these small, because the metadata path for file systems is not DAX, so it still does 4K metadata block IOs through these legacy file systems. Okay.
So I was recently joined NASA again for the third time, and I was doing a build for a new thing called PBS. And my build died, and it didn't die for anyone else. And it turned out that they had given me a user ID of 900 million. And because of POSIX compatibility, the data structures inside the tar code only allowed for user IDs of 2 million. What organization would have more than 2 million?
Yeah, 2 million should be enough for anybody. Yeah.
So, since POSIX compatibility is this way, this bug's going to remain. So it's like, is this stone too heavy to keep lifting and carrying along?
Well, there's a whole conference in itself. Yeah, no, but you lift that stone because you want to bring along like your COBOL applications that are written by people that aren't alive anymore, and you have no idea, you have no ability to rewrite it. Like the legacy buys you something. I mean, like x86 is successful mainly because it says you can run 1980s DOS on current CPUs, and it kind of just works. So I don't know. I think there's like POSIX compatibility has to be there, but I think there's room for new file systems to come along and do things. But like we've been doing just DAX for 5 years. Like a file system for people to gain confidence in it would be 5-10 years to get people gain confidence in it. So there's a lot. I think the attractiveness of maintaining compatibility and incrementally improving things just always keeps winning out, because you got to bring the legacy along.
I mean, when POSIX was created, we had a lot more operating systems. Oh, we got fewer.
Yeah.
A couple. Maybe time to portability.
Yeah, I think Linux to some extent has become a standard unto itself. Like there's POSIX and there's Linux, and people are starting, and so Linux has been bending those lines towards what it does and making that the API. But yeah, it's a good point. I think it went in the back before you. Yep.
I was going to say compatibility. I worked at Microsoft for a while. I had something called the Windows 2 program that didn't work. on Windows, I think Vista or 7. So I called up the person who I even talked to about that, assuming that they're missing no, the senior developers hours on web-based tech to help these guys get the Windows 2 programs. So that's why they have the enterprise market that Apple doesn't have, because Apple changed it a couple of times. They're not resource good for this stuff. I don't know how it works, but they keep it working somehow.
Over time.
I have two comments. The first is just an opinion. You mentioned that x86 runs ancient code. I can almost guarantee you there's a significant number of complexity to carry that code.
Yeah, there is.
And it adds to the latency of development of every new feature. Perhaps that's also one of the reasons why it's so many so hard. I don't know. But I actually, if I was with an Intel, I would push for throwing away all of those transistors and using it for a different purpose. Okay, at some point, we're going to come up with it.
I think that was called titanium.
No. I wouldn't go that far.
Okay.
I think developing the legacy doesn't mean inventing new.
Right.
So that's just my opinion.
Yeah.
I was wondering, from hearing your description of how this whole thing went about in Linux, this sort of software development for the democratic process doesn't seem to be working.
It worked.
It took too long. Did your the latency of your development get hidden by some other longer latency path in this whole process?
Well, I mean, it always helps. It always helps to have the hardware arrive around the time when your software is done, and the software was still going, and at the same time the hardware was still going. So that made a high pressure situation a little bit less pressure. That it wasn't like that people were shipping this stuff today and missing this. Does the process work? I think I would put it a different way. Not that, like, the point is not that, hey, if you want to deploy something new and you think you can conceive it and you want to deploy it in 6 months, you can't do that. It's more the lesson to take is the opposite. That if you want to do anything significant in Linux, you had to start early, like way early, or earlier than you think you need to. And this really only helps everybody, because, like, I mean, nobody likes writing documentation. If you can get your hardware developers to write the documentation early enough for you to implement the software way before the hardware arrives, that's like the best scenario. So I think as much as I'd like Linux to go faster and be able to say, hey, I conceive of this is going straight in, I'd like it. I also like the pressure, being able to say, hey, if you want this done, you got to give me these specs way earlier. So I think there's two sides to it. Like in the back there.
I understand that MapSync is primarily designed to ensure that block allocations in files are persistent and safe, but that's not really metadata.
That's not the only metadata there is, right?
And time bits, times on what indicate the last read and writes, but load and storage structures, of course, will not update those times. Is there a solution for that? Is there one there? A solution that doesn't destroy the performance of load store access.
Yeah. It's approaching pony territory, but I think the expectation was that people that want to do direct map things are also foregoing crisp time update time things. Can you force it to happen? I'd have to go look to see if you get accurate.
You can't even force it to happen with normal files on your memory method.
Okay.
Right? All bets are off. You don't want to take the fault on every storage when every other file. So A time is not going to show you the correct thing from that.
Yeah. About the only thing I can think of is basically to mark it read only again, and so that you retake another write fault, and then on write faults you'll sync the metadata again. But
Nobody wants to. They have performance.
fundamentally PMEM very addressable. So how do you think you can block devices and somehow wrong?
It does seem wrong, and this goes back to the whole debate about is PMEM storage or is PMEM memory? And
What about happy medium and reducing the size of the block to something like a hash line size?
well, yeah, I mean, but the block doesn't actually exist. Like when the IO request goes down to the driver, all it's doing in the backend is just a mem copy, and it could be a byte-aligned mem copy. So the blocks really only there for addressability for the file system, but the update granularity is still just bytes to cache lines.
So when you flash a page, then it's only writing hash line size?
Yeah. So when you flush a page from, like, if you treat it as a normal block device, you flush a page internal to the driver. It's just a 4K mem copy that can be interrupted at. It's the whole page. Right. If you're using block I/O, but so what Dax does, the other piece I didn't show was if you do a read system call unaligned to a page, what the old path would do would pad it up to a page and read a page from disk and give you that. What Dax does is short circuit that and says, hey, I'll just get the physical address and get the linear kernel address, which was just an addition operation, and then you just do a mem copy. So Dax basically cuts out even sectors or page granularity from the I/O path.
Maybe something,
Oh, good.
just to point out, I mean, this is all related to file systems on top of persistent memory, which you don't have to do as an application developer. You can go straight to the raw persistent memory device and do whatever you like on it.
Yeah.
User space. Right. So this is just the service the kernel's providing that as an application developer, you can just skip and get away from it.
Yeah.
That requires knowing what you're doing even more than you did.
Yeah, we invented something called device DAX, which is just a character device file that you can mmap and do whatever you want with. But because you can do whatever you want with, then you get yourself into trouble. So at least it's off on the side. There's no file system. There's no file system. People make angry because there's no file system, and you can do whatever you want. But also at the same time, you're responsible for everything. Yeah, you're responsible for everything. Yep.
The actual block was 256.
No.
I mean, if you write 72 bytes, it's actually read the other rest of the block. No.
Depends on the hardware. Depends on the
There's no block size, but it's a byte addressable model. The fact that some architectures are doing cache line I/O at 64 bytes on Intel, but there are NVMe products out there that are.
No, I was talking about specifically DC Optane. I saw that somebody said, well, the black blocks are 256, so if you read 100 bytes, it's really read.
Yeah, in the current, the shipping product, the ECC block is 256. But again, that's something you shouldn't depend on because that's a micro-architectural detail that will change.
But I shouldn't depend on it, but if that makes it faster and it happens to be right now, then that's not bad. I mean, as long as it'll still work if it's software.
Yeah, we kind of went back and forth on whether we should make that discoverable, to be honest, because, it complicates applications. And so currently, we didn't make it discoverable. That funky,
There's a funky way, but yeah, it's not exactly what, because you want like this is the I/O size that has to arrive by the memory controller to not trigger a read modify write.
But even then,
it's
different things. It depends how it integrates the memory controller with the cache.
That's what you have to ask. That's why you have to ask.
It's totally architecture dependent, and it's going to change. The most important is the failure atoms. If I wrote it, what went fail out? Right, and that is not reflected by the access, sectors.
No, I know, but say for performance reasons, the performance things I saw said reading 64 byte record and reading 256 byte records took the same amount of time.
Yeah.
Well, I know which one I would prefer to optimize my code for, so I get 4 times as much data.
But that could change.
No, what I'm saying, but
Yeah.
I'd like to be able to say how big is it, and I will use that.
No,
size.
it's a fair request. Yeah, definitely a fair request.
Yeah.
So Andy, you said that it will change.
Yeah.
Can you tell us what it will change to?
It's definitely changed to a number different.
Depending on whether the media gets better or worse.
Yeah, I take on my public relations advice from Andy, yeah, about how to talk about Intel details, yes.
Newsflash, 137 bytes.
Yeah, nice bed number. Okay, well, thank you very much.